You've made it through Chapter 8, in which we covered basically steam power plants, the basic Rankine cycle. But you do recall everything that you did in Chapter 8 involved the phase change substance, mostly H2O. And so now we're going to switch gears and we're going to move into Chapter 9. So let's look at what's going to be covered in Chapter 9. In your textbook, Chapter 9 is entitled Gas Power Systems. But very traditionally, the material that we cover in Chapter 9, we call air standard cycles. So I want to give you a roadmap of where we're headed and also help you prepare to switch gears from phase change substances into cycles that are basically dealing with air as the working fluid, as the substance. So here's a roadmap of what we're going to cover. We're going to start out by modeling. We're going to come up with thermodynamic mathematical models in which we're modeling internal combustion engines. And a lot of people have a lot of interest in internal combustion engines. We're going to be using the substance we're going to use to model our thermodynamic model is the ideal gas air, working fluid. And so we're going to start out with piston and cylinder models because we're going to try to model the diesel engine cycle. Some folks have some familiarity with that. The spark ignition cycle that we call the Otto cycle. A whole lot of people have experience with spark ignition or gasoline engines. And then a third model is a combination model of these two that we call the dual cycle. So that's going to be the early part of Chapter 9. Once we get through modeling internal combustion engines, we're going to switch gears within the chapter and we're going to model what's called an external combustion engine cycle model. And classically, that's going to be the thermodynamic model for gas turbine engines. And what we're going to do is we're going to put together a set of steady state, steady flow open systems, and we're going to build a thermodynamic model that describes the basic gas turbine engine. We call that the Brayton cycle. So here's a visualization of what we're going to do in Chapter 9. Over here on the left-hand side, we're going to be modeling internal combustion engines. And so it turns out that this top left image, well, that's a diesel engine. The bottom on the left, well, that's going to be a V8 gasoline spark ignition system. Over here on the right side of the slide, all three of these images represent some type of gas turbine engines. This is a stationary gas turbine engine. You can see a shaft coming out, and it's going to be driving an electric generator. It's a power plant. Okay, this is a Rolls-Royce Trent 1000 gas turbine turbofan engine, and this image is the classic depiction of a basic gas turbine engine in your textbook. So quickly, how is the first law of thermodynamics different for this set of models compared to this set of models? Think in your mind, how is the first law, energy balance, how is the first law of thermodynamics different? I hope that in your mind you remember over here, we've got a closed system. Our model is going to be a closed system. Look at this, a piston and cylinder. Over on this side, do you see that we've got m dot, we've got mass flowing into this engine and mass flowing out of this engine. So we've got an open system, steady state, steady flow, basically one inlet, one outlet. I hope in your mind, without going through the details, you say, yeah, I know the difference. There's some differences in the statements of the first law for these two categories of systems. Let's recap a little bit about things we already know about ideal gases, and then remember air is a subset of all ideal gases. What do we already know? Let's think in our minds of You think in your mind, what do you already know? How can you describe what governing equations, what fundamentals describe ideal gases and particularly air? Let's go through that. Well, let's see, things we all know. Let's see, R, that's the gas constant for a specific ideal gas, isn't it? That's R bar over the molecular weight. You've got that in your head. You don't need a formula sheet for that. How about the ideal gas equation of state? You've got that in your head. I hope you remember PV equals MRT. Okay, I hope you got that in your head. And then remember the definition of specific volume. Identical statement is P times little v is equal to RT. And you can solve, if you're interested in finding little v, you simply use algebra to solve for v is RT over P. If you're interested in pressure, P, you solve for P is RT over V. All these are identical equations. They're identical fundamentals, aren't they? But you know that ideal gas equation of state in your head. Do you recall the definition of specific heat, C sub P and C sub V? It's for an ideal gas, they're defined in terms of an ordinary derivative. C sub V is du dt and C sub P is dH dt. And you say, oh, I sort of remember that, but I don't recall what I did with it. Well, what you did was you separated out that differential equation to solve for delta U and solve for delta H. And so do you see that whenever you're trying to figure out delta U, you're going to use the integral of CV dt from state 1 to state 2. And if you're interested for some reason in trying to find delta H, you've got the integral of Cp dt. Thus, the two different C sub V, two different specific heat expressions that you use those depending on what you're seeking to find, what you're trying to get a numerical result for. Here's another valuable identity that, by golly, I sure do hope you know in your mind, in your head. For all ideal gases, C sub P minus C sub V is equal to R. And do you remember the definition of little k? Little k is called the specific heat ratio, and that's C sub P over C sub V. And so k is going to be a constant whenever C sub P is a constant. Okay, so these are things that I hope we're simply reviewing that you've already got in your head. Going to be key things to remember and use in Chapter 9. Okay, quantifying delta U and delta H. How do we do it for an ideal gas? For any ideal gas, delta U is the integral of CV dt, and delta H is the integral of Cp dt. But what happens if C sub V and C sub P are constant values? They're just numbers, okay? A constant number. Well, we can simplify, notice my dashed line here, delta U for constant specific heat is simply CV delta T. And delta H is simply Cp delta T whenever the specific heat is a constant value. And we're going to be jumping back and forth between having Cp and Cv are constant and Cp and Cv are variable throughout this chapter. Another thing that we covered very quickly in Chapter 6, and that's for an ideal gas. Notice my yellow text boxes. For an ideal gas that has constant specific heat, Cp is constant, Cv is constant, undergoing an isentropic process. Now, what was isentropic? That's a reversible and adiabatic. Reversible and adiabatic process, PV to the K is constant, where K is Cp over Cv. And so I've shown in my videos, it's pretty easy to derive these. Now, you might call them formulas, but these are fundamentals. So a restatement of PV to the K is constant is these two expressions if you're trying to find T2, which we're going to be in Chapter 9, and you know T1, and you know the pressure ratio P2 over P1, you've got a handy expression to solve for T2 for reversible adiabatic, ideal gas, kind of like air, and constant specific heat. And similarly, there's another expression that you can easily derive using algebra to solve for T2 as a function of the volume ratio, V2 over V1. Okay, so we're continuing on. Things we know, let's see, about air. Air is a subset of ideal gases, isn't it? What do you know about air? Hopefully in your head, the molecular weight of air is 28.97 kilograms per kilomole, or 28.97 pounds mass per pound mole. R for air. Well, that's R bar over the molecular weight, and that turns out to be R is 0.287 kilojoules per kilogram degree K, or 53.34 foot-pounds force per pound mass degree R. You may not have this in your head yet, but if you choose to go to graduate school and do graduate work in this type of area, ideal gas and air area, you're going to be getting that into your heads. Think about ways to model air. Two ways to mathematically model air as an ideal gas. You can choose, or you may be directed to, treat Cp and Cv as a constant number. Or you may decide to, or be directed to treat air having variable specific heat, kind of like a formula. Well, what do you do in those two cases? What do I do? If you're going to have specific heat constant, Cp and or Cv constant, you're going to go to table A20 and look up a value, a single value for Cp and or Cv. You got air, and you're directed or you decide to use variable specific heat, then you're going to be using table A22 to look up thermodynamic properties of air for variable specific heat. So that's sort of a decision tree. And notice in my green text box says, get guidance from your instructor. So I can't tell you how to solve problems. You have to go to your instructor or in class, have a discussion about how will we handle specific heat model for air. That's kind of important. Here's a recap of back to chapter 6. Wow, it's a long time ago. Back to chapter 6 in section 611.2, they talked about air. The author talked about air, and it was talking specifically about a pressure ratio and some E to the S0T divided by R. Yikes. And so there was a lot of discussion about that. The one thing I'll point out that back in chapter 6, this expression over here, E to the S naught T over R, that's called P sub R. Now that's different than that compressibility factor stuff. This is different than trying to figure out Z. Totally different. Okay. And this is called P sub R. You say, well, what is this going to do for me? When you have air, it turns out that for air undergoing an isentropic process with variable specific heat, it turns out that P2 over P1 equals PR2 over PR1, isentropic process. And you say, well, okay, where am I going to get these PR values? You're going to get these PR values that are a function of temperature only. It's talked about in chapter 6. You're going to find those in table A22. Find PR values in table A22. The key thing to remember here is that these PR values only apply to processes that are isentropic, reversible adiabatic. And so to drive that home, I've tried to draw in, here's an example. You see it, this is an example TS diagram for an isentropic process. TS diagram, isentropic process going from P1 up to P2. So this is just an example. And so my process is going to be state 1 to state 2I. And when this is the situation, when you have air with variable specific heat in an isentropic process, P2 over P1 equals PR2 over PR1. That's going to enable you to solve for PR2. Similarly, little v2 over little v1 equals VR2 over VR1. And these are tabulated in table A22 for air, for the ideal gas, air. And these are going to be very valuable to you as you're working through homework problems, quiz problems for Chapter 9, and test problems for Chapter 9. Going to be very important for you. Here's a screenshot of table A22. So this will be the example of when we've got air as our working fluid, all of Chapter 9, okay? Notice here, how's table A22 designed? Well, we've got a column of temperatures, and you see this is sort of like two tables in one. You see, we've got the left-hand side, we've got temperatures in the first column, enthalpy values in kilojoules per kilogram, internal energy values in terms of kilojoules per kilogram, S naught values, which you're not going to be using much, but over here and notice here, divided off columns, it says PR and VR. You're going to be using that a lot, but notice here, it says when delta S equals 0. So these two columns that are blocked off are only applicable for isentropic processes, reversible, adiabatic, okay? And then when we come over to the right-hand side of table A22, you see that this block here that I'm trying to circle with my cursor, it's the same idea as what we have in the left block. We simply continue temperatures going up, 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 and up, because what they do is they fit table A22 basically on one or two pages of text. So that's what that's all about in terms of sort of the two basic column blocks of table A22. All of these thermodynamic properties for air are functions of temperature only. It's an important thing to remember. And so I'm going to repeat this. This stuff is so important, it's worth repeating without words. So what I'm trying to suggest is that all of that information, wow, the first 12 slides in this video were basically review. Okay, now, so don't be embarrassed if there's material there that you don't remember or you're a little hazy on. That's okay. But do be aware that many of the fundamentals that we're going to cover in Chapter 9, we've already covered in this class. And so I do want to suggest that you're using your head as a bank of fundamentals that you've learned. And so this is an opportunity to improve the deposits in your bank of fundamentals that you've already got in your head. So you're trying to minimize your use of a formula sheet. Really want to try to encourage you to minimize your dependence on formula sheets. And this is so important that I thought I'd make some more screenshots out of Chapter 9. So this table 9.1, it's pulled right out of your textbook, and it is a review. It's similar to the review I gave you in the first 12 slides of this video. So if you don't like the slides, you can go to your textbook and refresh your memory on what am I doing with ideal gas? What am I doing with air? Here's the ideal gas equations of state. Remember, in problem solving, you're always trying to quantify what is delta U or what is delta H. And remember, it's a decision tree. You've got to decide, will I model my ideal gas or air with constant specific heats? If so, here's the fundamentals for delta U and delta H. Am I going to model my air as having variable specific heat? Notice here, it's like a paragraph. It says, go to table A22. Same, it's arranged a little better and more succinctly than my slides, but it's the same fundamental, same material. Same idea here is in terms of looking at changes in entropy and in fact dealing with isentropic processes. And here we go. And so this is near the bottom of that table in your textbook dealing with isentropic processes. Well, look at that. You say, well, look at those formulas. Those formulas are given in the book. You can derive those formulas. These aren't just formulas that are empirical formulas at all. They are restatements of the fundamentals of isentropic process, reversible adiabatic, with an ideal gas and constant specific heat. And over here, these are the same fundamentals for air, ideal gas, undergoing isentropic process with variable specific heats. So this is a delightful summary of the fundamentals you're going to be using throughout the rest of Chapter 9. And I see commonly used for air standard cycle analysis. And you're going to be doing nothing in Chapter 9 but analyzing cycle performance. That's what Chapter 9 is all about, cycle performance. And one thing I didn't put in my slide, but worth mentioning here. So the recap here for this video is you're already familiar with the fundamentals for analysis of these processes. They're involving ideal gases. Now, don't be nervous. It is not necessary that you know all of this stuff. You've got it all in your memory banks. You're just ready and raring to go. Chapter 9 is going to enable you to refresh your memory to get better and better at this analysis. And one thing that just popped in my mind as I was talking here is, what is cycle analysis all about? What are you driving at when you're analyzing a cycle for performance? Analyzing a cycle for performance. Doesn't that tell you that basically what we're going to be doing in Chapter 9 is we're going to be evaluating the thermal efficiency, the energy sought over the energy that costs for a bunch of cycles that you're going to be introduced to. This is going to be practical application after practical application. And so the idea, I know that some students, I'm thinking even 50 years ago, including myself, I said, I don't see any practical applications of this. This piston and cylinder stuff, I don't see practical applications. I do have to tell you, then once I finished my degree and got out working for a living, I started seeing nothing but practical applications for this material. So I hope this gives you an idea and some incentive for working hard and keeping up with your homework assignments in Chapter 9 and beyond. So I hope that helps. And in the subsequent videos, we're going to get into problem solving and modeling these air standard cycles.